Tree diagrams, what we're talking about today. You guys are going to learn another way to visually represent the different outcomes of an event. Tree diagrams are useful for problems where there's more than one event that can occur. So for example, you have a bag of marbles and you would draw out 3 marbles, okay? A tree diagram would be a great way to represent basically your first pick, your second pick, and then your third pick, okay? The easiest way to talk about tree diagrams for you guys to learn about tree diagrams is essentially through an example. So we have one here about Samuel. Let's get down the important information, of course, the questions. And that way we can go over tree diagrams. So the probability that Samuel, a key member of the school's archery club, hits the bullseye 0.8. Samuel takes 2 shots. Assume that success with each shot is independent of the previous shot. Okay, here that definitely matters because if you think about it, if you take a shot and you miss it or make it, you know, it can kind of like mess with your psyche, but they're basically telling you that his first shot has nothing to do with his second shot. So you want to find the probability that he hits 2 bullseye, he hits only 1 bullseye, or he hits at least 1 bullseye out of his 2 shots. Okay, the bullseye is that part that's like smack dab in the middle. So a tree diagram essentially starts with a node, which is a point, and then next you'll draw lines that represent the branches for your tree. Okay, the branches essentially represent the different things that can happen when Samuel steps up to shoot his archery arrow, right? He's either going to, what are the outcomes that can happen when he steps up and he's getting ready to shoot? When he shoots, what's going to happen?
Either bullseye or not bullseye.
Exactly. He's either going to hit the bullseye or not hit the bullseye, which means that there are 2 different outcomes that can happen. He either hits the bullseye or he misses the bullseye. The number of branches you have depend on the number of outcomes that can occur, right? Now on the branches go the probability of these things happening. So we're told that he hits the bullseye 0.8. That says probability of 80% hitting the bullseye. So that means that 0.8 is going to go on hits a bullseye. So that means the probability that he misses is going to be 0.2 because the probability total has to add up to equal 1. So then that's, if this is 0.8, the one at the bottom has got to be 0.2. And this is the first part of your tree diagram. This represents his first shot. How many shots does he take? 2. And so whether or not he hits or he misses it, he's taking another shot, which means that what outcomes could happen?
Again, hit or miss on both of them.
Exactly. So that means from hit and also from miss, you're going to have 2 branches as well to represent the fact that he's either going to hit the bullseye or miss the bullseye on his second shot, regardless of his first shot, because they are independent of each other. So because they're independent as well, that means there's no change when he steps to shoot the second time. What's the probability that he hits?
0.8.
Misses,
0.2.
and that's regardless of whether he hits or he misses. And so this would be the tree diagram that represents the different outcomes when he steps up and takes his 2 shots. How do you work with the tree diagram to find the probabilities? Well, to find the probability that he hits 2 bullseyes, you essentially are going to go along the branches, right? His first shot, he hits, so that's 0.8. And he hits it again, that's 0.88 again. You multiply those 2 probabilities together to get the probability that he'll hit the bullseye both times. What's 0.8 times 0.8?
0.224.
Okay. And to get that, we just went along the branches, hit and hit. Now we want to find the probability that he only hits 1 bullseye. Well, how can that happen if he only hits once?
He misses the second.
So you can hit the first one and miss the second one, or
You can miss the first one and hit the second one.
exactly. All right, and since they're independent events, we're gonna multiply again along the branches, and then the two different outcomes that could happen, we're gonna add them together. So he's either gonna hit, then miss, or he's going to miss, then hit. So we're gonna do 0.8 times 0.2 plus 0.2 times 0.8. And what is that
About 60.
for both?
Yeah.
Oh,
So then
32.
0.32. That's gonna be a probability that he hits only one bullseye. Last but not least, he hits at least one bullseye. Keyword, at least. That means he's either going to hit, miss, miss, hit, or hit, right?
Mhm.
So we can take each three of those probabilities and add them up, or we can find the probability that he what? What's another way to do it?
He got no bullseyes.
He hits no bullseye, and then we can do the complement. 1 minus miss, miss. Because if we do the complement, that means he has to hit it at least one time. So 1 minus, he misses, that's 0.2 times 0.2. So then 1 minus 0.4 is, so the probability that he hits at least one bullseye is 0.60 or 60%. And sorry, let me not say percentage because it did ask for probability. That's always the decimal, not the percentage. A bag contains 5 green and 6 red balls. If 2 balls are taken out successively without replacement, what is the probability that at least one green is chosen? And what's the probability that a red is picked on the first pick, given that at least one green is chosen? Okay, here we can do another tree diagram to represent this situation. As we're picking out 2 balls, okay? One that's gonna happen right after the other, that's what they mean successively. Even if they don't say successively, that's something that you assume that one ball is picked, then the next ball is picked, okay? But another key part of this is the word without replacement, which means what?
Can't be replaced.
Meaning that once they pick out the ball, they're not gonna put it back in. So you have to also keep that in mind when you're creating your tree diagram. I have my node. How many branches am I gonna have off the first node? What are the outcomes that can happen?
2. Wait,
2, what are they?
green and red.
Green and red. So they can reach in, they can pull out green or a red ball. Now, if they pick green, what's the probability of picking green?
5 out of 11.
5 out of 11. There's 5 green out of the total pack. And what about red?
6 out of 11.
There we go. So that represents our first pick. But our second pick is going to change depending on what we picked the first time, because it says without replacement. If I pick it, first off, what are the outcomes that can happen when I reach in for a second time?
Green and red.
Green or red. So if I pick green first, how many greens are now left in the bag?
4.
4.
4 out of
Out of what?
10.
10, because if you took a green out, now there's not 11 balls anymore, it's only 10. But how many reds are there?
Wait, do we round it or not?
No, we leave it like that. I mean, if you want to reduce, you can.
5 out of 10.
Not for a red.
Oh, that's right. 6 out of 10.
6 out of 10, because, well, one, the branches need to add up to be 1. But because I picked green the first time, all 6 red marbles are still there. Now, if I pick red the first time, how many green marbles are there?
5.
5, because I didn't pick any of them, so all 5 are still there. But if I pick a red the first time, how many are left for the second time?
5.
5, because I've gone down 1. And of course, our branches have to add up to equal 1. So this will be the tree diagram to represent us picking 2 balls out, one after the other without replacement. The denominator changes based off of the fact that you're not putting the ball back in. Okay. Actually, yes, let's reduce this. 4/10 reduces down to what?
2/5.
2/5, 6/10.
No, I'm sorry, 2 over, wait, 2?
No,
3/5.
5. All right, ladies, where y'all at? What about 5/10?
1/2.
1/2. So then we have 1/2 again. Okay, so these are my different outcomes. I can go green, green, then green, red, then red, green, and then red, red. You don't have to write out the different outcomes that you can have. Sometimes I do it, sometimes I don't. Okay, and so, well, no, I won't do that. So I want the probability that at least one green is chosen. At least one green is chosen. How could that happen?
Everything but the last one.
Everything but the last one. So I can take green, 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 red, red, green, add them up together. Or
you could do the complement of not a single green, so the RR.
Or I can do the complement of RR. And to be honest, it's a little easier. So to do RR, that's going to be 6/11 times 1/2. Okay, remember, anytime we go along the branches, we multiply. So the probability of picking red the first time was 6/11. Probability of picking red the second time was 1/2. So then that turns into 6/22. 1 minus 6/22 is what?
It is 16
Over 22. Yep. How's that reduced?
Divide by 2, so 8/11.
Very good. So the probability of you picking at least one green is 8/11. That's the same probability you would get if you did green, green, plus green, red, plus red, green. Now, part B says, find the probability that a red is picked on the first pick, given that at least one green is chosen. Keyword, given that. What does that imply?
Oh, that line formula thingy.
The line one, that's conditional probability. So I want the probability of red being picked first, given that we have at least one green.
Isn't that the third option?
Say again?
Isn't that the third option?
But we have to consider well, that would be technically this here, but that's not just our final answer. Okay, we want, if I use the formula, I want the probability that red is first and it's intersecting with at least one green. So then that would be what you said, that would be that option. But then I have to divide it by the probability of it being at least one green. Didn't I figure that out in part A?
Yep.
Sure did. So my denominator is 8/11 because that was the probability of getting at least one green. But the numerator is the intersection between red first and at least one green, which would be this option right here. So I need to do 6/11 times 1/2 for my numerator. So that'll be 6/22 divided by 8/11. How do I simplify that? How do I simplify a fraction within a fraction?
Keep, change, flip.
So that'd be 6 over 22 times 11 over 8. How many times does 11 go into 22?
Twice.
How many times this, or what number goes into 6 that also goes into 8?
Shoot.
2.
So it'd be 4 and 3. So then my final answer for this one, the probability that a red is picked given, on the first pick, given that at least one of them is green,
3 over 8.
3 over 8. So that's how you do conditional probability with the tree diagram as well. Toby is a rising star of the school's tennis club. He found that when he gets his first serve in, the probability that he wins the point is 0.75. When he uses his second serve, there's a 0.45 chance of him winning the point. He is successful in getting in his first serve in on 3 out of 5 occasions, and his second serve in on 3 out of 4 occasions. So, tennis. For those who've never watched, who don't know how the game works, I'm going to set up this tree diagram for you to help you out. In tennis, a player has 2 opportunities to get his serve in. Okay, so when he steps up to the line and he does his first serve, 2 things can either happen. Either he's going to get the point or get the ball in, or it's going to go out or maybe in the net. Okay, this is on his first attempt. Okay, now if he gets the ball in, the game is played back and forth, right? And then 2 things can happen. Either he's going to win the point or he's going to lose the point. Everybody follow me so far?
Yes.
Now, if he gets it out or if it goes into the net, then he has a second serve that he can use. So again, he gets it out, okay, he steps into the line and he serves again. So 2 things can happen again. He can either get it in or it can go out. Okay, so this is on the second attempt. Of course, if he gets the second serve in, they play it out and he's either going to win or lose the point. But if he gets it out on his second serve, then he just loses the point altogether. Okay, so essentially in tennis, you have 2 chances to get your serve in. If you don't get it on the first time, you have a chance to get in on the second time. But if you get it out both times, you lose the point altogether. So this is like the template for the tree diagram. Now let's fill in our probabilities. The second sentence says he found that when he gets his first serve in, so when he gets his first serve in, the probability that he wins the point is 0.75. So that means up here, it's going to be 0.75. Which means if he gets his first serve in, what's the probability that he loses?
0.25.
0.25. Because again, the branches have to add up to equal 1. Now it says when he uses his second serve. So he's got to use his second serve. There's a 0.45 chance of him winning the point. So if he gets it in, he's going to win 0.45. Which means he's going to lose
0.55.
0.55. He is successful at getting his first serve in on 3 out of 5 occasions. So if he gets it in on 3 out of 5, 3/5 is going to go here on this first branch. But to keep it consistent, what's 3/5 as a decimal?
0.6.
There we go, which means he's going to get it out 0.4.
4.
Good. And his second serve in on 3 out of 4 occasions. So his second serve is going to be point what? For in. 0.75, because that's 3 out of 4. And then out 0.25. The only branch that doesn't have any probability is here on the lose, and that's going to be what?
100.
100% or 1. Because he's going to lose the point if he gets it out. Questions on how we set up the tree diagram? Let's find the probability that the next time it is Toby's turn to serve, he wins the point. Don't let this right here throw you off. The next time just literally means like, okay, it's Toby's turn to go. So what's the probability that when it's Toby's turn to serve, he wins the point? How could he win the point? Looking at this tree diagram.
You can go in and then you win, or you can go out and in, then you win.
Exactly. He can either, the ball can go in and he wins the point, or it can go out the first time, in the second time, and then he can win the point. What do I do to these two probabilities?
Add them.
I add them. So I need in first, and I'm going to multiply that by him winning. That's 0.75. Remember, anytime we go along the branches, we multiply. Then if we go out first, then in, then win, this is what we'll have. So we multiply and add those together, we'll find the probability that on Toby's next serve, he's gonna win the point. Figure this out for me, please.
0.6075.
Points, what?
I got, I don't know if I did this right, but I got 0.0675.
I got 0.585.
Okay, so we got two different answers. All right, so let's look at this one. So 0.6 times 0.75 plus 0.4 times 0.75.
Yeah, I got Lucas's answer.
All righty. So then it says, that's our answer for part A. So then for part B, it says, given that Toby wins the point. Given that, what does that mean?
Probability. No, I mean condition.
Conditional probability. So given that he wins the point, what's the probability that he got his first serve in? So this is how we would set it up. First serve in, given that he wins the point. Well, that will be the intersection between first serve in and win over the probability that he wins the point. Don't we already know the probability that he wins? Is what we found in part A. And a lot of times IB will do that. Like part A or part B will be used for like that conditional probability later. But what's the intersection between first serve in and win? Huh? How do I find that? First serve in and win. What's the probability he gets the first serve in? The 0.6 and then wins. So I multiply those two together and that's going to be my numerator. Because that's the intersection between winning the point and getting the thing in. So there's going to be 0.6 times 0.75 divided by 0.585. Remember, alpha y equals option 1 gives us that fraction. So don't forget about that little feature.
It's not necessarily.
It's not, but you gotta be careful just in case. So around the three significant figures, what is it?
0.769.
0.769. That's the probability that he wins the point. He got his first serve in. Here we have an IB problem. I like this problem a lot because it incorporates a few aspects from probability that we talked about so far. It involves the Venn diagrams for part A and part B, but then part C, which you don't see yet because it's on the other slide, deals with tree diagrams, okay? So this is a nice little review of some of the stuff that we've done so far. This is in a class of 21 students, 12 on a laptop, 10 on a tablet, and 3 own neither. The following Venn diagram shows the events on a laptop and own a tablet, the values P, Q, R, and S represent these number of students. I do want you guys to try A and B first before we do it together. So I'll give you a few minutes to do that. And then we'll do part C as well.
And see, this is where we have a teacher. I am a terrible explainer.
All right, what's the value of P?
3.
It is 3 because that is the neither. That's the ones who are in the universal set, but not with the actual device. Now, what's the value of Q though?
4.
The value is 4. And you know that because if you add 12, 10, and 3, that equals 25. When you add the 12 from laptop and the 12 from tablet, you're counting the people who own both devices twice. So when you subtract 21, you get the number of people who have both that overlap. So Q is 4, which means that R has to be what?
8.
8, and S has to be
6.
Okay. You say that fast. All right, and you can always check yourself by adding up all 4 regions. 3 plus 8 plus 4 plus 6 does indeed equal 21. So now that you have that, it says a student is selected at random from the class, from the entire class. So that means my denominator is going to be 21 for both. What's the probability that student owns a laptop?
12.
Out of 21. That reduces, what number goes into 12? That also goes into 21.
3.
So 12 divided by 3 is
4.
and
7.
thank you. Now we're going to find the probability that student owns a laptop or a tablet, but not both. So how many own just the laptop and just the tablet?
8 and 6.
14.
Which would be a total of 14. What number goes into 14 also goes into 21?
7.
So 14 divided by 7 is,
2.
and then
3.
there we go. Now, this is a long response one, so there's more to this. There's a C, there's a tree diagram, and there's a part C double I. So I'll give you guys a second to write this down. One thing too, you see how this says do not write on this page? That's because like in your long response ones, there's never like lines underneath, which means that they're always done in like a separate booklet where you do your work, okay? I've had a chance to get you guys customized to that because you guys are on campus, but that's what I used to do. I used to give these little packets, they look like this, where you would essentially do your long response questions on.
You could try it one time if you could print it out.
I can do that. I can definitely do that. And another thing too, is this copy and complete. If it ever says that, you've got to copy down the entire visual and then complete it. Don't ever complete it in the actual problem. 2 students are randomly selected from the class. Let L be the event the student owns a laptop. Okay, so it's very important that you know what each of those letters are because sometimes they won't write it out all the way. So L means own a laptop, which means L apostrophe means what?
Complement.
Doesn't own a laptop. So what's going to be the not the numerator? What's going to be the top branch probability?
12 over 21.
Very good, because it has to add up to equal 1. I know here, 11 out of 20, 9 out of 20, we're good there. But you have a second student that's picked, okay? How many students are left for that second student to be picked? What's the denominator for both of these?
20.
20, okay? So if a student who does not own a laptop is picked, then how many students who do not own a laptop are left to be picked?
8.
8. And what does 8 out of 20 reduce down to be?
8 out of 20?
Yeah.
2 over 5?
Very good. So that means how many own a laptop are picked, or could be picked for the second time?
12.
And that reduces down to be
3 out of 5.
3 out of 5. Very good. course, I will copy this over because copy is key, but. Now, this is write down the probability that the second student owns a laptop, given that the first student owns a laptop.
So wouldn't that be the 12/21 times 11/20?
That'll be 12/21 times 11/20. And the reason why it is a write down is because you're given that the first student owns a laptop. Well, that can only happen 12 out of 21 there. And so you just multiply it to, or actually,
Wait,
Sorry.
don't we need to get the conditional probability thingy?
we still would need to use conditional probability if we're gonna do it this way. So we want second student owns a laptop, given that the first owns a laptop, which means we need the intersection between the second one owning and then the first one owning, all over the probability that the first one owns.
Mhm.
So this will be the numerator, but then the denominator would be 12/21 because that's the probability that the first one owns a laptop. And what do you notice between the numerator and the denominator?
It can cancel.
The 12/21s can cancel because we're multiplying in the numerator. So my final answer is just 11/20. That's why it's a write down, because we actually could have just pulled it straight from the tree diagram. Because given that the first student owns a laptop means we are looking from this branch, then we want the probability that the second student owns a laptop. So the answer would just be the 11/20. But here it is using the formula all the way out, simplifying there. This is non-calculated, so you definitely don't want to multiply 12/21 by 11/20, because then it could be confusing.
Agreed.
Question, Nikki?
So if we align basically everything with the formula, wouldn't it be 11/20 multiplied by 12/21?
For the numerator, but then the denominator would still be the probability that the first student picked owns the laptop.
Okay, because I was just like confused if I got the thing matched up right.
And that's how you use tree diagrams.
I have a question.
Yes.
So why is it in the second student? Why is the first one 12/20 and the second one is 8/20?
Oh crap. So here, remember, complement of L means they do not own a laptop. So the reason why this one was 8/20 was because originally you had 9/21 students who did not own a laptop when the first student was picked. Well, once that first student gets picked, I can't pick them again.
Okay.
So that means you pull them from the group.
Okay, thank you.
You're welcome.